In a previous video, you want to refer back to that. I talked about the displacement current with regards to a capacitor, and we ended up calculating that the charge density JD was equal to epsilon naught dE by dt. You might want to refer back to that just to refresh your memory on that, but we're going to be using this in this tutorial. So when we discussed Ampere's law previously, we assumed that the current I was a conduction current. However, experimental evidence shows that in situations that include time varying electric fields, the displacement current ID, as we previously defined, must also be included in Ampere's law. That is, using Ampere's law in problems involving the relation of magnetic field to its sources currents, we must treat conduction and displacement currents on an equal footing. Both act as sources of magnetic field. Thus, the general form of Ampere's law is written like so. It includes both the conduction current, IC, and the displacement current. Here is an example of the role displacement current in Ampere's law in a magnetic field calculation. So this figure is a cross-sectional view of two circular conducting plates of radius r, so I've put the radius r here, separated by a narrow gap in a vacuum. They are, in other words, a parallel plate capacitor. If the gap is small compared to r, then the E field, this E field here, caused by the charge distribution, is confined almost entirely to the region between the plates and is uniform. Suppose we want to calculate the B field at some point in the mid-plane shown in the figure, and want to work out the B field somewhere along this thin line. In principle, this field can be obtained by applying the law of Biot and Savart to the conduction currents in the plates and the wires leading to them. Because of the radial currents in the circular plates, this is a fairly involved calculation. So instead, we may take advantage of the axial symmetry of the situation and use Ampere's law. So that's what we're going to do. There is no conduction current in the region between the plates, but there is a displacement current. From the definition of displacement current proved previously, the total displacement current out of the left plate is equal to the conduction current into the plate. Also, by symmetry, the B field lines are circles with centres on the axis. Thus, at any point on a circle perpendicular to the axis passing through the points such as A and B, so we've got point A and point B here, the B vector has the same magnitude and is tangent to the circle. Because they're all uniform, this B vector and this B vector, if we work out its magnitude, they're going to be the same and they're going to be tangents. Now at point A, the B vector points out of the page, and at point B, it points into the page, as indicated by symbols dot and the cross. Remember, we multiply any area here by JD, we're going to get the current in that area. The total current ID for this capacitor is JD times pi r squared of the plates. As we remarked above, this must also equal the total conduction. So this whole ID current, displacement current, equals this IC. Thus we can write ID equals IC equals pi capital R squared JD. Therefore we can rearrange that to write JD is IC over pi r squared. We may find the magnetic field at a point in the region between plates at a distance r from the axis. Such a circle then passes through points C and D. The total current enclosed by the circle is obviously the current density times its area. So it's this times the area of that circle, that circle that sweeps around that part. It's pi r squared. Now we've got that, we can apply the integral in Ampere's law. It's just b times the circumference 2 pi r of the circles. Plugging this value back in there, and we've got the 2 pi rb over there. We get 2 pi rb equals u more, and then we've got the id, which is this term here. Obviously the pi and the pi cancel here, so we end up with IC r2 over r capital R2. So then we got r squared over capital R squared IC. So that's what we got. And then we can rearrange then to get B. Given any point between these two plates, we can find the magnitude of the magnetic field. This result shows that in the region between the plates, B is 0 at the axis, increases linearly with distance from the axis. A similar calculation shows that outside the region between the plates, B is the same as though the wire were continuous and the plates not present at all. This calculation bears a strong resemblance to the one in the example where we used Ampere's law to find the magnetic field inside a cylindrical conductor. You might want to go back and check that one. In a certain sense, we can think of the space between the conducting plates as a cylindrical conductor, but there is a displacement current. Thus, it should not be surprising that this final equation here is in fact identical for the one that we did for the cylindrical question we did before. So that's very interesting. The role of displacement current as a source of magnetic field can be expressed in a different way by using the concept of electric flux. Now remember, the electric flux is basically the electric field times the area, so we can rearrange the E here and get it in terms of flux per unit area. And remembering our current density equation, epsilon naught dE by dt. Now, if we just replace the dE by flux per unit area, then we end up with the current density equals epsilon naught d flux per unit area dt. Now, if we pull, obviously the A is a constant, we pull that outside, the A will be underneath. Now, remember here, we've also got a current per unit area, so if we multiply through by the areas will cancel, and we just end up with the displacement current. So the displacement current then equals epsilon naught times the rate of the flux change. Thus, in empty space where there is no conduction current, in other words, IC equals naught, Ampere's law may be rewritten: the closed path integral of B dot dl equals mu naught epsilon naught times the rate of the flux change. We will see later on that this equation bears a close resemblance to another relation, Faraday's law, which describes the electric field induced by a changing magnetic field. The fact that displacement current acts as a source of magnetic field plays an essential role in the understanding of electromagnetic waves. A changing electric field in a region of space induces a magnetic field in neighbouring regions, even when no conduction current and no matter are present. This relationship, first proposed by Maxwell in 1865, provides the key to a theoretical understanding of electromagnetic radiation and of light as a particular example of this radiation. So we'll turn to this later.